All right, so we're continuing our section 3 notes for chemistry here in chapter 5. We have already talked about atomic radius and ionization energy, but we just have to continue with that and finish some things up because some people are gone and need to pick that up for us. But otherwise, like I said, we've done atomic radius. We've gone through the reasoning for that, why atoms that are down and to the left are going to be the largest and the ones up and to the right are going to be the smallest. Remember, when you're doing a vertical comparison, you're talking about shells. When you're doing a horizontal comparison, it's got to be a proton issue. And then we went on to ionization energy, and it turned out I had the same ideas, right? That pull from protons can hold on to those electrons better for some than others. So when horizontally I compared things, right, the more protons you have, the more likely it is to hold on to that electron, the less likely it is for it to lose it. Right? So the things with the highest ionization energies were up and to the right. They don't want to lose electrons. It takes a lot of energy to pull electrons out of those atoms. Whereas vertically, again, it has to do with how close the electron is to the center of that atom, because that's what affects the attraction the most, not the amount of protons. So just be careful when you're doing your reasoning. But otherwise, as we continue, electron affinity is really the same thing as ionization energy. It's just the opposite idea. Instead of losing an electron, well, how likely is it for this atom to gain an electron? Right? So electron affinity is just the energy change when an electron is acquired by a neutral atom. Right? Most would release energy because that electron had energy and it lost energy to be caught. But some atoms do have to be forced to gain that electron. They don't actually want the electron. So when we have this electron affinity, you can actually make an atom gain an electron. It just won't keep it for very long. Right? So those are the ones that would actually release energy instead of absorb, or excuse me, those are the ones that would actually absorb energy instead of releasing in the process. But otherwise, only nonmetals tend to gain more than one electron, and they typically do so to gain a noble gas configuration, which should make sense, right? You want to fill those shells to make them stable. So our periodic and group trends, again, is just picture-wise thinking about your periodic table, right? We should have exactly the same ideas as we had before. So when I look at ionization energy, I'm going up and to the right, and it's getting bigger, right? Ionization energy and electron affinity are essentially the same thing. As I'm going from left to right, I'm going to have an increased affinity for those electrons, and that should make sense because of the attraction, right? As I go from left to right, and if I'm comparing things with the same number of shells, then the more protons you have, the more attraction there is, right? So I have the same reasonings as before. More protons gives you more pull, right? You can grab onto a brand new electron that didn't even belong to that atom originally. Whereas up and down, right, again, the ones above are more likely to gain an electron than the ones below, right? Because of what we talked about before. It's easier to catch an electron when that electron's going to fall into a shell that's closer to the center, right? Again, the closer you can get that electron to the center, the more attracted it's going to be. So the affinities, again, go up as you go up a column because the electrons in mind are closer to the center. And therefore you would have more attraction again, right? And again, this is the same idea. I put those things together and I can start to understand that I have this stair step for a reason. I have metals and nonmetals that have different properties for a reason, right? Nonmetals that are up and to the right they have high affinities for electrons. They're more likely to gain electrons than lose them in reactions, whereas the metals down and to the left, they have low ionization energies, low affinities. It's easier for them to lose electrons than gain electrons. So the whole idea of this is to really put that together and understand why nonmetals and metals have different properties. Otherwise, we also have to talk about ions and deal with ions in this section. So you have cations, anions. These are just terms to refer to positive and negative ions, because you can either gain or lose electrons to get a charge. The one thing I do usually look at for this is in terms of trying to remember these two terms. When I see that T in cat ion, I always am visualizing a positive sign, right? There's a cross in that T, just like a plus sign, right? Those are the ones that are positive, whereas anions are negative. Otherwise, ionic radii, once an atom gains or loses electrons, it does actually affect the size of said atom. So what we're talking about here is not necessarily one atom versus another, which we can actually do, but an atom that's normal and neutral versus its ionic version, right? That's what we're trying to compare in a lot of cases here. So we have these periodic and group trends again, but also just before and after that sodium atom, that oxygen atom, right? What's it going to be like before and after it gains or loses an electron? So we already know what's going to happen to a normal radius as I go from left to right and from top to bottom. And the same things are actually going to be true in general for ionic radius, but it also depends on how you look at it, because the rows are all shifted. That's what makes this kind of hard, right? So it depends on what that thing wants to do as to what's going to happen to the size of it. Because if I have a metal like sodium, remember sodium on your periodic table, right? It's a metal. It's in group 1. It has 11 protons and 3 shells of electrons, 2 electrons in this first shell, 8 more in a second shell, and then 1 final electron in this outermost shell. And sodium, being a metal, is more likely to lose an electron than gain an electron, but it should actually be pretty obvious what's going to happen to the size of the sodium atom when it loses said electron. Because as soon as that one electron, that lone electron in that outermost shell is gone, as soon as it loses it, now it doesn't have 3 shells anymore. Now it only has 2 shells. So for metals, when they lose electrons and they turn into these positive cations, because when you're losing an electron, you have more protons than electrons now, right? Metals shrink when they ionize, when they become ions, when they lose those electrons. So sodium before and after, there is going to be a difference. A normal sodium versus a sodium ion, the normal sodium is going to be bigger, and it's going to be bigger, because it has more shells, right? So that's what happens with a metal. So otherwise, we also need to know what happens with a nonmetal, because nonmetals tend to gain electrons, not lose electrons. So let's say we have that oxygen this time, right? So I have 8 protons. I'm going to have 2 electrons in this innermost shell. I'm going to have 6 more electrons in a second shell. And what it's really going to want to do is it's going to want to gain a couple extra electrons to make 8 total in that second shell, so it has the same number of electrons as neon, right? Because as soon as it has the same number of electrons as neon, it can be stable, right? That does end up giving it a negative charge. This is an anion now as opposed to a cation. But what I want to know is what happened here, right? I had an oxygen that turned into an oxide ion. Which one's bigger, which one's smaller? And this time it's not as obvious. I didn't gain a shell, I didn't lose a shell. I have the same number of shells. But what we did talk about before should help us with this, right? There's two different things going on here. I have protons that are pulling in on those shells, pulling on those electrons, bringing them closer to the center, as close as they can get to the center. But I also have electrons that obviously aren't collapsing to the center for a reason. They actually pull outward slightly. And the reason why that shell has a certain size to begin with is because those two forces cancel out, right? So that pull in and pull out have to cancel out so that those electrons don't just collapse to the center or escape. So I have electrons that pull out and protons that pull in. And when I talk about oxygen versus oxide, the only difference between this oxide ion and what I had before is I have a couple extra electrons. And electrons pull outward, right? So if I have a couple extra electrons, both of which are going to pull a little bit more out, that actually means that my oxide ion is going to be bigger. It's going to have a larger radius, than my normal oxygen. And the reasoning this time is not about shells and it's not about protons, right? It's because it has extra electrons. And those electrons pull outward. Making that atom larger than it was before. So your anions are bigger than they were as neutral atoms, right? So when they gain electrons, those nonmetals gain electrons to be happy, right? If it's a negative ion, it's bigger than it was before because it gained electrons, those electrons pull out. If it's a positive ion, if it's a cation, if it's a metal that lost electrons, you're going to have a smaller radius as an ion because it's going to have one less shell than it had before. But otherwise, the ionic radii, when you compare different things, right, I can compare nitrogen, oxygen, and fluorine, right, all of which could be ions with these respective charges, -3, -2, -1. The difference being, right, they all gained electrons to look just like neon, essentially, right? They all wanted to have the same number of electrons as neon that doesn't have a charge currently and never does have a charge because it's already stable. But they all have the same electron configuration as neon. They have the same number of electrons as neon, but they have different numbers of protons. So that's what we come to with our comparisons. When we look at those different ions and we compare nitrogen, oxygen, and fluorine, right, as I go from, I wanted to do blue here. As I go from left to right, are those things getting bigger or smaller? And it's the same as it was before for normal radius, right? A nitrogen ends up being smaller than a fluorine because it has fewer protons. So as I go from, right to left actually, so I'm going to make my arrow that direction, these radii, these ionic radii get larger. And the reasoning is that fewer protons lead to less pull. Just like before. Whereas up and down, top to bottom, right, I might look at things a little bit differently. Because again, oxygen versus sulfur right below it that will also end up with a -2 charge, right? Sulfur is still going to be bigger than oxygen for the same reason as before, right? Sulfur is going to have one more shell than oxygen did, right? Just like, well, excuse me, this sulfide ion is going to have one more shell than this oxide ion, but they both just have one less shell than they normally do. So I actually have the same things going on there as I go from top to bottom and I compare these things, right? The things towards the bottom have a larger radii because of the shell issue, right? So as you go down, there are more shells, and more shells make those things automatically bigger. Now, where this gets a little bit more confusing though, and we're going to have to work with this a little bit more to explain it a little bit better, but I can compare that sulfide ion to let's look at something over here in the same row, to a sodium atom, that same sodium atom we were talking about before, right? But comparing those two things isn't actually going to be as easy as you might think, right? Our general trends only work when you're comparing metals to other metals and non-metals to other non-metals. Because if I compare sodium, this metal that lost an electron to be happy, and this sulfide ion that gained electrons to be happy, right? Sulfur is gaining electrons to be like argon, not like neon, right? So it wants to be like argon, not like neon. Sodium wanted to be like neon. So when I compare those two things, and this is a little bit weird at first, but sodium essentially looks like neon, that sulfur ended up looking like argon. Excuse me. So I'm not really comparing sodium and sulfur, I'm comparing neon and argon. Neon is definitely smaller than argon because neon has one less shell than argon, and so does that sodium compared to the sulfide. So although normally, as I go from right to left, when I compared fluorine, oxygen, and nitrogen as ions, right, that radius gets bigger. Sodium is actually smaller than sulfide, but that's because it didn't do the same thing. It lost a shell. Sulfur, the sulfide ion, still has the same number of shells. In fact, it gained a couple of electrons and got even bigger than it was before. So you can only do simple comparisons with things that are close together, right? Non-metals compared to other non-metals, and metals compared to other metals. Because if you put magnesium right next to sodium, magnesium with a +2 charge is actually going to be smaller than sodium, just like you could predict using our general trend here. Because they both have the same number of shells, they both are trying to look like neon. But magnesium has more protons than sodium, so it pulls in more, right? And what ends up happening here is I actually can compare magnesium and oxygen now too. Magnesium and that oxide ion, those two ions are comparable. Magnesium is going to end up being smaller still than that oxide ion because nitrogen, oxygen, fluorine, sodium, magnesium, all 5 of those elements wanted to look like neon to be happy. So they all have the same number of shells. Magnesium has the most protons. Nitrogen has the fewest. So nitrogen should actually be the biggest of those 5 elements in their ion form. So it's kind of confusing. We'll talk about that a little bit more. I can draw it a little bit more later just to explain it better. But for right now, just understand the general trend and definitely understand why metals get smaller when they become ions and why nonmetals get bigger. Otherwise, we'll do comparisons more later because that can be kind of confusing. Otherwise, the other part of this section we need to pick up, right? We have these valence electrons that we're going to start talking about. Those are the electrons available to be lost, gained, or shared in compound formation. And we're going to talk about how we're combining S and P electrons for main group, right? When we talk about valence electrons, we generally speaking ignore the D sublevel. So when I had that test question last chapter where I forgot the D sublevel, that's because I was thinking about the valence electrons. Once you fill that D sublevel, it doesn't really matter anymore. So when I talk about magnesium, it has 2 valence electrons because it has 2 electrons in that S sublevel. But sulfur has 6 because it has 2 in S, 4 in P, 6 total, right? But selenium below sulfur also has 6 because I don't care about those ones that were in 3D, right? They would have come before 4P. So it's a little bit confusing at first, but just understand that that D sublevel, once it's filled, those electrons actually that shell actually drops down in energy and becomes part of that inner shell. And so we just don't worry about it, right? So when we talk about valence electron, that's going to be S and P only, right? So make sure you know that. Electronegativity is the measure of an ability of an atom in a compound to attract electrons from other atoms in the said compound. So electronegativity is something that we're going to use to determine whether something is polar or nonpolar. So if you guys remember from biology, I talked about how a substance that you're pretty familiar with, water, is very polar because oxygen pulls on electrons better than hydrogen does. So it actually causes a separation in charge in this molecule, which is what makes it a polar molecule to begin with, right? But how I know that this is polar and how I know that that oxygen is negative and the hydrogen is positive is because oxygen has a greater electronegativity. It pulls electrons better than hydrogen does, which actually is pretty much the same thing as affinity, right? So if I go backwards to electron affinity, right, as I go up and to the right, my affinities are the greatest. I'm going to have the exact same trend in this case, right, as I go up. And as I go to the right, I have higher electronegativities. And it's for the same reasons as before, right? If something has a high affinity, it can grab onto electrons that it didn't have previously. If something has a high electron affinity, it's also going to have a high electronegativity. It's going to pull electrons from other atoms in a molecule, right? So I have the same trends actually. We don't really need to go through the reasoning for this because it's the same reasoning, right? As I go up and to the right, I have higher electronegativities. Non-metals, generally speaking, have the highest electronegativities. Metals, on the other hand, have extremely low electronegativities because not only do they not attract electrons very well, but they also don't make bonds with other atoms. So we're really going to look at these electronegativities later. We're going to use those later. But when we find out that fluorine has the highest electronegativity versus other atoms, right? So fluorine has a higher electronegativity than oxygen, the nitrogen, and the carbon. That has to do with the fact that fluorine has a smaller shell, and the electrons are closer to the center, and there's even a bigger apparent charge in the center for fluorine than oxygen, than nitrogen, than carbon. So it's going to have a higher electronegativity. It attracts electrons better. So we have all the same ideas as before. It's not new. It's pretty much the same. Otherwise, this last slide, properties of D-block metals don't vary very much. So read into that by thinking, okay, I don't care about that on the test. So don't worry about it. Otherwise, ion formation, we're going to talk about that specifically, but we're going to do that in class probably. So even if you weren't in class because you were at 1X, right, we're definitely going to talk about the ion formation. And that does matter. We're going to learn why some atoms have weird charges when it's all said and done. And then some atoms also have two possible charges. So we're going to end up talking about ions more. We're going to memorize names for ions and know their charges. And we're going to have to understand that sometimes they have more than one possible charge. So we'll deal with that later. Otherwise, this should be good for now.